Hi, I'm John Foro from AST. Today I want to talk to you about a diagnostic class. I know as of late you've seen me doing a lot of EV classes, hence the whole social media name of Electron John, but I got my roots in this industry doing engine drivability type of classes. So today's subject matter is going to be on drivability. There's a lot of stuff that I see on different social media pages and different forums that I'm a part of where people are maybe having a little bit of misconception on how to diagnose some different types of problems. So what I want to do is I want to kind of keep this kind of generic, but I call this advanced system testings. You'll see that there's many roads that will lead you to the same destination. Just like in life, there's many different paths we can get from point A to point B, many different routes we can take, so to speak. So there's really no wrong way of doing this, as long as we originally or eventually arrive at our destination. But our goal here today is to try to get inside the mindset of a diagnostician. So, a lot of times people will ask me, hey, what's your favorite go-to tool or whatever the case happens to be? And I always tell people that most of my diagnostic processes involve two primary tools. One is going to be a scan tool. Obviously a scan tool, without a doubt, that's going to be my starting point with just about any kind of diagnostics, unless it's, a headlight's not turning on or something like that. And then eventually I'm probably going to break out a scope for a lot of the different drivability type of problems. And I'm not telling you that that's what you have to do. I'm just giving you an insight as to how my mind works when I'm faced with the drivability type of problem. I try to get as much information as I can from my scan tool before I ever open the hood on a car. And if the vehicle comes in, and I'm just going to throw an example out there that says the vehicle's running rough, whether or not there's a trouble code associated with it doesn't bother me at all. I'm going to go through the scan tool screen, and in that one example that I gave you, your problem's going to turn out to be either something with the ignition system, the fuel system, or an engine mechanical problem. If it's running rough, whether there's a misfire, whatever. So we're all professional technicians, and we all know, hey, I could start off by doing a actual compression test, doing a cylinder leakage test, vacuum gauge test, hooking up a scope to the ignition system. I could do all these tests. But we want to do it more logically, and we don't want to take a holistic approach and test all these different systems. We want to get to the system that's causing the fault. So I'll start with the scan tool. I key in on 6 main lines of data, so 6 different PIDs. Those 6 PIDs, a lot of times I'm going to generic or global OBD2 for these, for the main simple purpose that I don't have interpreted data that if there's a hard fault that we're having a substituted data from different car lines or anything like that. These 6 lines of data are always found on every type of car on the global side of OBD2. Those 6 lines of data that I'm concentrating on are the temperature inputs, the O2 sensors, both pre and post CAT, my load sensor, so whether MAP, mass airflow, whatever, my demand sensor, which is throttle position, and my RPM sensors and fuel trims, both short-term and long-term. Now, if I zero in on looking at those 6 main lines of data, and as we go through this little presentation here before we start turning it over live to this vehicle, you'll kind of understand what my thought process is and what I use those 6 lines of data for. Now, I'm not saying that if I have a specific diagnostic trouble code. So if I had a specific diagnostic trouble code, say for an EVAP system related problem, well, I might look at some of those lines of data, but by the same token, if I have a code, I'm probably going to be using a different whole diagnostic process because the computer has generated a code for me. I'm talking about if it's a misfire code or if it's just a drivability complaint type of scenario that I'm trying to use these 6 lines of data here. So let's take a look at what I use some of these different PIDs for. So my temperature PID, I'll use that for rich running type of scenarios. So maybe the complaint comes in and it smells like rotten eggs or something because it's running rich, or maybe the fuel trim is telling me that it's trying to take away fuel for whatever reason. I'm also looking at my temperature PID for restricted exhaust, so an engine breathing type of ability. So if I'm looking at my intake air temperature sensor, for instance, and I'm comparing that to similar type of inputs, so like coolant temperature, maybe barometric pressure, stuff along those lines, and I see that my intake air temperature sensor, no matter where it's located, whether it's in an intake manifold, inside of an air cleaner housing, I don't care where the manufacturer put it. If I start to see that getting too high, right? So if I'm looking at my scan tool and it's got lack of power type of complaint, or maybe it's running rough, or whatever the scenario happens to be, and I look at my intake air temperature and I see that that's 180 degrees, we'll just throw that figure out there. Well, if I'm still alive and I'm still actually able to comprehend what I'm doing on my scan tool, it can't be 180 degrees. I get it. There's under hood temperatures, and maybe if you're in the desert and stuff, you know, but realistically, that's an extremely high intake air temperature reading, you know, and if it's higher, then obviously everything follows suit with this. So where's it getting that extra temperature from? It's getting it because that hot exhaust gases, which could be, you know, 600-700 degrees of Fahrenheit, can't make its way out the tailpipe, so it's finding its next hole. In this case, happens to be the throttle plates, which is how we're actually increasing that intake air temperature sensor value. I'm also looking at my RPM sensor, right? My RPM sensor, that's telling me conditions for, you know, crank signals. Here's a prime example of this. Let's say it's a no start and the car cranks over fine. Well, we all know that we need an RPM signal. We need an RPM signal so that the fuel injectors can start spraying fuel, the spark plugs could start firing and everything else. If the car, and most of them do, if the car manufacturer supports just a cranking RPM on your scan tool, you can actually kind of rule out if the computer is seeing that input. If it's saying that it's got 0 RPM and the car line supports the cranking RPM, like again, most car manufacturers do, well then that's going to be one of the first things I want to turn my attention to. Now before we get too much further ahead, I always want to back up a suspicion, right? So we'll use the first one, the temperature, as an example. If I thought, looking at that scan tool with the intake air temperature sensor, if I thought I had a restricted exhaust because that temperature was too high, I'm not going to stop there. I'm going to look at other PIDs to help me verify that that is in fact what is the problem. Because what I'm basically trying to accomplish here is when I get my butt out of the driver's seat and I decide to start doing pinpoint testing on the system, I want to verify and I want to justify any type of time it's going to take me to do a series of tests. Now, those series of tests in my head, I've got, if it was a breathing type of scenario, maybe I want to do a compression test, a cylinder leakage test, whatever the case happens to be. I'm going to come around, I'm going to open up the hood. Now, my diagnostic path may change depending on how hard it is to do some of these tests. So maybe one of the tests I wanted to do for that scenario would have been an in-cylinder pressure transducer test, right? It'd be a great test to do. But if I open the hood and I determine that, hey, half the cylinders are covered by the intake manifold, or possibly maybe it's a Triton 4 and I didn't want to risk the spark plugs breaking off as I try to unscrew them or whatever, I still want those test results, but I may come up with another way of doing it that's easier for that particular application. So let's continue on looking at some of those other PIDs. So I'm looking at my O2 sensors, pre and post CAT. Now, if it has an air-fuel ratio sensor as of late, all the late model cars, again, this is one of the benefits of going into global OBD2 because I can still look at O2 sensors the way that I was accustomed to seeing it on the data stream PIDs. So what am I using my O2 sensors for? I'm using those to help me diagnose a misfire problem, a fuel issue problem, vacuum leaks or exhaust leak problems. Basically a rule of thumb, and we'll come back to this here in a little bit, but a rule of thumb, if I look at my post-CAT O2 sensors and they're higher or greater than 600 millivolts with the upstream being lower or normal, that's usually an indication, it's running rough, that's an indication that it's an ignition type of problem, right? Now I'm going to look at some of the other PIDs to verify that, but it's an indication that the reason why this car is running rough is because it's ignition related. If it's lower than 200 millivolts, then it's usually an indication that it's a fuel related problem. And that opens up a whole different series of tests that I'm going to do. My ratio sensors, if I was on the OEM side of the data stream, I'd be looking at my pumping current, right? So, if it's up, if the pumping current value is higher, that's usually indicating lean. If it's lower, that's usually indicating rich. And lambda, a lot of the different car manufacturers support lambda now, especially on global OBD2 side. Lambda less than 1 is indicating a rich condition. So obviously higher than 1 is going to indicate the opposite. My throttle position sensor, well, this goes along with the actual strategies that the computers have in it. So one of those strategies could be clear flood mode. And in clear flood mode, a lot of cars support that. If it sees that the cranking RPM is low, but the actual throttle position sensor or pedal position sensor, if it's a newer type of car, is actually saying that it's at wide open throttle or pretty close to it, well, now the computer is going to think that you're in clear flood mode and it's not going to turn the fuel injectors on. So the car won't want to start, right? So does it match the load? That's another thing I look at the TPS for. If I have a mass airflow or if I have a map sensor, whatever the car manufacturer has, in theory, if I stepped on the gas pedal, there should be no lag time for all of a sudden those throttle plates open up for that incoming air past, let's use a mass airflow as an example, to actually pick up that increase of airflow. If there is a lack of time that occurs, usually it's going to be like a hesitation type of complaint, stumbling, lack of power type of complaint, something like that. Well, that's a pretty good indication that there's a problem with the mass airflow, possibly something as simple as just a contaminated hot wire on the mass airflow sensor. And then obviously I'm going to be looking at that sensor for any type of possible glitches as well. Again, I'm always going to be backing it up by looking at other lines of data. So then I also have 2 more PIDs that we talked about as my 6 go-to PIDs, right? If you watched any of my my electric vehicle classes, you know that in those types of vehicles I have 20 go-to PIDs. But in drivability related stuff, way easier, got only 6. So I'm also looking at fuel trims and my load sensor. So again, my load sensor, whether it's mass airflow or MAP, doesn't much matter. Some of the indications that I get off of that is there any type of pirate air getting inside the engine? Is there a vacuum leak that's causing this to have to run rich or run lean, or whatever the case happens to be? Are they possibly contaminated hot wires associated with it? The calibration of the mass airflow sensor itself, right? So we'll call it, again, we're going to go into greater detail with some of this stuff as we go on here. Right now, I just want to focus on my 6 main PIDs and how my mind interprets these PIDs. So my fuel trims, short and long term, that's obviously telling me a good insight as to whether the system's running rich or lean. Fuel system issues, if it's a fuel system related issue with the fuel trim, that should go ahead and affect the entire dynamic range of operation, right? So let's say if I have a weak fuel pump or a restricted fuel filter, we'll keep it as simple as possible for this quick explanation. It's not just going to be weak or restricted at idle or off idle. It's going to have a lack of fuel pressure the entire dynamic range. So this is how I can start using some of this stuff so that when I get out of the driver's seat and start doing pinpoint testing, I know the series of tests that I want to do. Again, it may change once I open the hood and see how hard it is to do, but as you go through and you kind of see the slide that we were talking about there, if it's ignition system related problems as opposed to fuel system related problems, that is going to affect fuel trims as well, but they're going to be minor type of corrections. You're not going to have a positive 25 or a positive, if you're on the generic side, positive 98%. If it's ignition related. That's going to be more of a fuel related type of thing. So this is going to be the 6 main PIDs that I focus the majority of my attention on. And if we understand this, right, so if I looked at the scan tool while I'm sitting in the driver's seat and we use that complaint of, hey, it's running rough, whether or not there's a P0300 code associated with it, it's either going to be fuel or it's going to be engine breathing capabilities, we'll call it, or it's going to be ignition. So which series of tests do I want to pull from my diagnostic arsenal to get to the root problem here, right? And then I want to do them as quickly and efficiently as possible that gives me the same type of test results here. So now when I open the hood on the car, it's not like I'm wearing a blindfold and have no diagnostic direction to go into. So what do I really need to diagnose anything? And I've said this for many, many years. You know, I'm old as dirt. I've been doing this for over 30 years doing training classes. You need a system or a circuit knowledge of how something's supposed to work. If you don't have that, you are handcuffing your diagnostic success, the outcome of the success of the outcome that you're trying to accomplish here. So if you have to, if it's a car line that maybe you're not familiar with or something, it would behoove you to maybe do a little bit of research on your information system. Maybe you need a wiring schematic, whatever the case happens to be. And then also, you need to understand PCM strategies, whether it's regarding mode 6 or just overall strategy. So what's a strategy? We'll keep it real simple for this quick introduction part here. We all know of a strategy called open or closed loop, right? So in open loop, it's when the car is first started, that oxygen sensor has to heat up to about 600 degrees Fahrenheit before it's ever going to go into closed loop, right? So in open loop, let's say, we're going to be looking at key inputs. So those key inputs are going to be a temperature sensor, throttle position, load sensor. You know, we're going to be looking at key inputs. We're not looking at an O2 sensor input because we're not even using the O2 sensors during open loop operation. So the reason why I chose that one as an example here is, let's say you get a customer that brings you a car and they tell you it has a drivability issue only when it's first started. And you scan it for codes. If that was your standard, you know, mode of operation there, you scan it for code and you see you got an O2 sensor code stored, well, that may be a problem and you might be able to fix that. But if all you did was fix that O2 sensor code, that drivability complaint is still going to be present because, again, the computer wasn't looking at that for that drivability condition. So again, your information system is loaded with all kinds of different system strategies and stuff. Mode 6, there's a ton of training classes that I've done over the years. There's a lot of information out there. I share with a lot of the different posts and stuff that I do. I share some of these strategies with you. So, you know, regarding mode 6, we'll use this as a quick example. This is something I did years ago. This is when Ford did not, well, you needed a secret decoder ring, right? So they would give you a hexadecimal code and then Ford would tell you to use some crazy decimal point thing and, you know, multiply it by each other to get a value that actually made sense to us. But it doesn't matter. Even if it did actually tell you, if we fast forward to a more modern day car, it would still give you the same type of information. So this one here is a Ford example and it's about an EVAP system, right? So it tells me that for this particular hexadecimal code, which was test identification $2C, it's testing for a 20,000 leak, so 2,000 model years and later, and there was a phase 2 test that it failed it for, right? So I'll just fast forward, there's 4 phases on those cars, right? So phase 2 is what failed on that EVAP system test. And it was an idle check, and it told me how the computer was trying to test it. And it was outside of that range, which is why it set that code, right? So again, if I go to another slide here and kept talking about it, I kind of would walk you through the most logical types of tests here. But if I had a generic code, for instance, say a P0440 for an EVAP related code, mode 6 could be very beneficial because if I saw that that code, that the phase of the testing strategy that it actually failed, so if I thought it was a 440, we'll just use, you know, backyard mechanic mentality right here. And people say, well, let's put a gas cap on it, right? Well, is it going to fix it, right? Now, you would know that if you understood how to interpret the mode 6 data. Because if it was a gross leak that was failing the large leak test, the small leak test, and the different phases that Ford had there, then you could justify the fact of, hey, it could be that the gas cap's missing or the gas cap's bad or whatever. But if it was a small leak test and you saw that it was done under certain drivability conditions, then that would rule out the possibility of a bad gas cap. So this is how our mindset has to think, and as we go through some of how we approach some of these different types of problems, it may help to see maybe a possible case study before we actually turn it loose on the actual car over here. So I'm going to do one quick case study. This is on a lack of communication type of problem, right? So if it's, whether it's CAN, LIN, I don't care what the network happens to be. We'll use CAN as an example. You know, on your screen you see that there's a good CAN high and CAN low signal being displayed right there. So in theory, your scope, if you have one, you could use a breakout box, go to terminals 6 and 14. You can pull the two signals over to one another. You're seeing the messages going between the different computers shared along the data bus communication lines, right? So we'll use as an example, this is an 06 Buick LaCrosse CXL. It was a no start, no communication type of complaint. It came into my shop one time. And again, it's not necessarily that the case study is what we're trying to teach you. It's the thought process that I have so that you can use this thought process when you're faced with whatever the type of case study happens to be that you're confronted with. So the customer called me up and they said, hey, I just bought this car. There's no warranty on the car. I already tried going back to the dealership. I took it to my other mechanic. My other mechanic, you know, replaced the battery because even though it cranked, it wouldn't start at times, but even though it would crank when it wouldn't start, you know, he said that I should probably start with the battery anyways, which doesn't make any sense to me, but whatever. And, you know, it's intermittent. Sometimes it'll start up, no problem, other times it won't. It seems like when it doesn't start though, it makes this loud pitch howling noise sometimes. And I'm like, yeah, you just bring me the car, right? So the car comes to me, you know, luckily the problem was there, it showed up and everything, but even if it wasn't there, I could go through and I could take a CAN signal waveform from my scan tool and I could probably have seen the problem, even if it wasn't showing up at the time. I'm not saying that's always going to be the case, but for this particular one, it probably would have showed up. So, you know, I went ahead, I verified it wouldn't crank, no lights are coming on the dash, nothing, right? Which maybe that's why the other mechanic said he wanted to put a battery in. I'm not sure what his thought process was with that. So, and I did hear a noise, and that noise was coming from the rear speakers on the vehicle. It wasn't constant, you know, it pretty much happened every time I'd have it into the cranking mode. So if it had a key, if you held the key over to crank mode, that's when you'd hear that noise. If you released the key, it would go away, which was weird, right? But, you know, I just used all my senses, all my human senses, and I just put that in the back for future reference, right? So I wanted to go ahead because I had no communication with my scan tool, and that's one of my go-to tools, as we said earlier. So since I had no communication, that made me say, okay, well, let me check the data bus network. So I hooked up my OBD2 breakout box, and I tried to get a waveform. Now, this particular vehicle was using J1850, right, which is another form of communication for those of you that are in the know with this stuff. But the signal should be with the key in the on position, as long as the network is awake, should be between 0 and 7 volts. And right away I noticed that on the J1850 line, that was the waveform I was seeing. So, you know, I didn't spend a whole lot of time setting up the scope. I could have stretched that out and saw the information packets a little bit wider and everything if I had checked like time base. I was just looking for a good go or no-go type of signal. And this was definitely a no-go type of signal because it never went low, right? That whole communication line was staying higher than the 0 volt threshold there. So I knew I had a problem. Now what the problem was, I don't know, and this is something that always bothered me about, you know, any type of communication type of fault was, you know, eventually if you followed a flow chart or something, it may tell you to start unplugging modules one by one, which would be okay if all the modules were easy to get to, but you guys know these modules are hid all throughout the car. You got to take all kinds of stuff apart on the car to get to them. So this particular system here used a shorting bar. So the shorting bar was located, used a couple shorting bars actually on this one, but the one that had the effect going with it was located underneath the steering column area on the vehicle. So I pulled the shorting bar down and I said, okay, so I got to remove the comb, right? So I'm going to remove the comb. That's part that actually shorts that splice connector out there. And I printed out a schematic. Again, I don't know how that system's wired, so I have to go to my information system and print out a schematic. And I see that there's a series of different modules on that particular splice, that shorting splice there. And I see that one of the lines of data going to that splice is actually shared by both the radio and an airbag system. Now, in my mind, right, I'm thinking in my head, I should start with that side of the shorting splice, right? Because the radio is making a noise, and plus, if you know anything about these cars, you know that the airbag is located underneath the passenger seat. A lot of times, carpet gets all saturated with water, and then it wants to corrode, right? But I said, no, I'm just gonna start logically with the numbers, so I started at the other end. And what I did is, when I removed that shorting bar, it took all of those modules off the network. I still had my lab scope and everything hooked up, and I used a set of jumper wires, and I put one module back on the network at a time, and I was monitoring for a good communication signal. Now, if I saw it going from, you know, the 7 volts down to 0 volts, I knew that that module, that circuit, I should say, was not the problem. So as I did that, going all the way up that ladder in that shorting bar, when I got to the last one, the one that shared the two, my initial gut reaction was I should have started from that end, but I wanted to verify them all. That's when I got the bad signal again. So I knew that it had something to do with one of those two modules or circuits. So just like anything, you'd want to check powers and grounds and all that stuff. But I figured in my head, well, let me just go ahead and disconnect one of those two modules. So this is where my first fork in the road came. Do I want to take the dash apart to get to the radio so I can unplug the radio? Or do I want to take basically the passenger seat out, pull the carpeting back, and do the airbag module? And in my head, it was a real controversy because I was having that stereo noise, right? So I almost took the dash apart, but I said, you know, from experience, let me go after the passenger seat. So I took the passenger seat out, and I noticed as soon as I was working on my hands and knees, getting to the bolts and everything, that carpet is extremely wet, which made me feel more confident at the time, right? So carpet was extremely wet, and as I peel the carpet back, the way how the floorboard's made and everything, there is like 1.5 inches, 2 inches of standing water on the floorboard. So now I'm thinking, hey, maybe this vehicle's been in a flood, whatever. I get to the actual airbag module, and this is what I found, right? So there's the picture of the original airbag module, and the one that I replaced it with is obviously higher up. And then the picture on the right is the actual faulty airbag module. So as soon as I saw that, I'm like, oh, this is definitely going to be it. But I unplugged it anyways, and then everything was normal again. So at this point, you know, you call the customer, you get the okay to do the job accordingly. So after it was all said and done, put the car back together. That's what that pattern was supposed to look like, right? But this was my mindset as to how to diagnose this. It all started with the customer call, and obviously verified the complaint. I hooked up a scan tool. That's always one of my first steps. When I had no communication, then I went to my scope. And then once I got my scope involved, I started to see the diagnostic process unfold in front of me here. So at this point, what I want to do is I want to kind of talk about what can I do with not necessarily looking at the data stream on the car, because those quick little silver bullets I gave you about, hey, you know, if it happens to be a misfire problem and you're looking at your post-CAD O2 sensor, what the value should be and stuff, I think you kind of have that. I want to visit the scope, right? So with the scope, if it's got an engine breathing type of problem, well, what could cause that, right? So I could open the hood. If I determine I had a mechanical problem, I could open the hood on the car, and like we said before, start off by doing a manual compression test, then go into a cylinder leakage test. The benefit to using an in-cylinder pressure transducer is technically I do both of those tests electronically at the same time by going directly inside the cylinder. I can see the valve train operation, plus I can see the overall compression. So That's a shortcut that I could choose to do if I wanted to. I could do those old-fashioned mechanical type of tests. Maybe I open the hood on the car and I say, hey, I want to do a compression test, but half the cylinders are covered by an intake manifold, but I still want to know if I got good compression. Well, maybe I do a relative compression test, right? As opposed to a mechanical compression test. So I have a lot of options available to me. I want to talk about the test results and what I use some of these for, because I'm just going to throw some different diagnostic scenarios out there and show you some of the advanced testing procedures you can do with your scope. So I've got up on the table in front of me here a series of different types of tooling and stuff. And here's a pressure transducer. So I've got the Pico one right here that's made to go inside a cylinder. And then it can also go to a vacuum hose or whatever else I want. And then I got the less expensive style. And this one here, I cannot put it inside of a combustion chamber because the pressure would be too high. So this one has like a little vacuum diaphragm inside of it. And if I obviously try to put 150 PSI of pressure through there, I'm going to rupture that diaphragm. But this sensor is a pretty universal type of sensor. I can put this in and measure lower types of pressure or vacuum readings, like in the exhaust tailpipe, possibly into a vacuum hose. If there's blow-by in the engine, which I'm going to explain all this stuff to you guys, I can get a lot of diagnostic test results with this style pressure transducer, which is a fraction of the cost of the big dollar Pico one, right? The Pico one is by far, one of my favorite ones. It's a go-to. It can do anything that I want it to do. However, if you're on a budget, it's not a bad idea to pick yourself up one of these. You could do all the same tests that I'm about to show you, with the exception of putting it inside the combustion chamber. For that, I would need the more expensive Pico version. Also, I have a couple little leads here. So these leads are very inexpensive. I got them right from AES Wave. These leads are invaluable. So basically, I've got a red one and a green one. The difference between them is the red one is for ultrasonic testing. The green one is for frequency. So if I had, let's say, a no-start type of complaint, well, with a modern day vehicle, right, it's probably got a push button start on there. I have to have the key fob inside the car. Also, it's probably got a little push button on the door handle that's supposed to unlock the doors as I walk up to it, all that kind of stuff. Anything that measures frequency on the car, I now can take my frequency style connector, hook it up to my scope, and I can get a lot of diagnostic test results. So for example, if I had a no start on a modern day car, I could have a bad battery, I could have a bad starter, I could have all the normal stuff. I could also have a bad sensor that's picking up anything from the key fob to the actual push button on the dash. How would I normally test that? If I didn't have that, I'd probably scan it for codes, maybe use topology screen, scan it for codes, and if I was lucky, I had a code to go on, right? But still, eventually you get to a point where, hey, does the transponder actually work in that push button, on the push button start system? Well, here's a great tool for being able to figure that out. I can have my foot on the brake in park and everything and just push that button, hold the little sensor in close proximity to it, and I should get a waveform on the screen. The ultrasonic one, that's great for any type of backup alerts, right? I'm not talking backup cameras, I'm talking about the little alerts that are beeping as you get closer to a brick wall as you're backing up or something like that. Or anything that emits an ultrasonic type of signal on a vehicle. And each one of these leads are roughly about the $30 range. And like I said, these are both made by Pico, but I got them from, AES Wave out of California, George and Carlos. Then, this particular sensor that we talked about earlier, I got this from Jarhead Diagnostics, right? So they got a website, you can go there, they got a whole host of different types of, sensors, 3D printed type of stuff. So this is a 3D printed case around my Pico transducer just to help absorb any kind of impact if it was to fall or something. So that's just some extra protection there. But none of this stuff is extremely expensive. And then I also have, for doing some other types of testing here, a few more different types of leads here, and this I got from a guy by the name of Joe Casey. Now I apologize, I don't know Joe Casey's website. I think it's something like joesautoelectric.com, but I could be wrong with that. Just Google search his name. But this is another very talented individual that I'm friends with within the industry. He's got a pressure transducer that you can use to hook right onto vacuum hoses and stuff. He's also got a frequency style sensor here that's made for picking up noises. So picture this, the customer comes in and they're complaining about, you know, hey, it's got a rotational noise and it's a wheel bearing thing. And you know, the types of noises that create a lot of bass, it's always hard for the human ear to differentiate exactly which one it is. It could be a knock sensor that you're trying to diagnose. It could be a wheel bearing. It could be any type of noise. These are really nice, very affordable, very high quality stuff. And then he's also got a little tool here, another little adapter that's made to test ignition systems, or basically things with magnetic fields that are collapsing, right? So most of the time you're going to be using it to test ignition coils and stuff. So I'm going to be using some of these things just as quick go-to tests as we go through there. So focusing our attention back on the PowerPoint before we get started on the car, some of the stuff I'm going to be looking for. I get a scenario, the customer says it's running rough. Whether or not there's a misfire code, I don't care. I could quickly verify if it is actually running rough, because if it is running rough, it's going to affect the exhaust pulses coming out of the tailpipe, right? Now, if it's a dead misfire, it's going to extremely affect them. So this is something I did real quick. I just walked to the back of the car, and I'm going to do it on camera here in a little bit. I put a pressure transducer in the tailpipe. I get a good go or no-go style test. What I'm looking for is uniformity on these initial tests when I'm using a pressure transducer. If I wanted to determine whether or not I had excessive blow-by in the engine, blow-by could be bad rings or whatever the case happens to be. Again, I'm looking for uniformity. So there's a picture of a good engine on the right comparing it to a bad engine. Now, again, this is a good go or no-go type of test. I'm gonna, on this particular car, I just got to get hooked up to the crankcase somehow. So they sell adapters. You can take the oil fill cap off and stuff. I just use the dipstick tube, right? 99% of the cars still have a dipstick on it, so I just pull the dipstick tube out, put the pressure transducer inside the dipstick tube to get this type of result. And the reason why these are go or no-go style tests is because if I got the waveform that's on the left that says excessive blow-by, we know that there's a problem because it's not uniform there, but I don't know which cylinder that is, right? So if I wanted to determine the cylinder that's causing the problem, I'd have to hook up a second channel of my scope. And I'd have to hook it up to something that's going to display firing order. So either the ignition system or the fuel system, a fuel injector or an actual, you know, spark plug or coil pack or something. And then as I go through here with the exhaust pulses, again, here's a picture of a faulty coil that's causing a problem in those exhaust pulses, right? And I can do the same thing by hooking up to a vacuum hose, and a vacuum hose is going to, in essence, give me a cylinder leakage type of test result because I'm seeing the opening and closing of those intake and exhaust valves. Again, the first test is just hook the pressure transducer up. One channel, quick go or no go. If I'm getting uniform results across the screen, I'm good. I'm going on to the next test. If I get something that looks suspicious, those scenarios I'm going to take some time and actually hook up a second channel to, say, an ignition coil pack or whatever the case happens to be. So I've got some firing order frame of reference. So when I start going through this, I'm going to kind of do it quickly on this car. When I start going through this on the car, I'm going to be using pressure transducers. I'm going to be using, you know, the ignition system adapters. I actually am going to be using the one from Joe's Auto Electric here, placed right on there, right off cylinder number 1. But I'm also going to be using an inductive current probe, right? And I'm going to clamp this around the ignition system as well. So again, it's not going to take a whole lot of time to get these test results. I can do the same thing for relative compression. If this is something that you guys kind of like, I want to keep this video as short as possible, but if you guys want more information like this, you can always put in the comments of, hey, we'd like to see some more advanced system testing strategies, and we can do a whole series of different types of tests. So what I'm gonna do, I'm gonna just go ahead and I'm gonna have my scan tool powered up right now. I'm gonna turn the scope on. Autel calls it the measurement screen. I'm gonna turn the scope on. My one channel, I already have the pressure transducer in the exhaust pipe of this car, so once I start the car up, I'm gonna get a pattern. I purposely chose a car that doesn't have a problem because I wanna show you what the good patterns look like, so you got something to compare for a point of reference to. So the guys that have seen me do a lot of drivability classes in the past know that a lot of times I'll use a Pico scope, maybe I'll use the ATS scope, whatever the case happens to be. So I wanted to choose a different type of scope for this particular video, so I chose the Autel scope, plus it doesn't hurt the fact that, you know, Autel gives me a paycheck every week as well. So I figure I'd give them some publicity here. Now, channel A is the default. If I hit the little button at the bottom that says Auto DC for next to the A, I can go in and I can actually set up my voltage scale right here. It's gonna default to auto just like most scopes on the market does. I usually just leave it on auto till I acquire the signal. Then I'll come back in here and change it so that I get what I wanna see on the screen. If I went down one for probe setting, here, the accessory kit that comes as an option with Autel, if I wanted to use an actual current probe or something, you'll see me do this as we go through these tests. I'm going to scroll through here and tell it that I'm going to use a current probe, right? And then if I had a component, so Autel does not make a pressure transducer, but if I wanted to use a pressure transducer for, you know, future reference in the future, I can always create a custom lead. And I would do that by the probe edit button down here. One last thing is if it ends up being a dirty signal, so it's got a lot of noise in the signal, Autel has the low pass filtering where I can turn on and adjust the filter amount per channel. I don't think we're gonna need to use the low pass filtering on what I'm about to do, but I'm just gonna kind of show you how I do this. So what I'm gonna do is I'm gonna start the car up. I'm gonna just have channel A on. We're gonna get a waveform. I'm going to make a couple little small adjustments on the screen as we go. Then I'm going to go ahead and turn on channel B, which I already have. Again, this is going to be Joe Casey's ignition input here. We're going to get a number one trigger adjustment here. So if there was a problem on a cylinder, I now have a firing order displayed. So we're going to make a couple adjustments on the screen once we turn channel B on again. And then finally we'll turn channel C on, which is a low amp current probe, which is going to the coil primary circuitry here for all 4 cylinders. This is a 4-cylinder vehicle. So I could select the driver for just cylinder number 1 if I wanted to, but I wanted to get all 4 patterns on there. So that's the progression we're going to make. After I do that, then I don't really care about the other 2 channels anymore. I'll probably turn those back off, and I'll just show you, since we talked about it, I'll show you going to, say, the crankcase, right? And I'll pull the dipstick tube out, we'll go in there, you'll kind of see the same examples of what we're talking about here. So I'm gonna go inside the car real quick. I'm just gonna start the car up. As you can see, in auto preset, it's trying to display a pattern for me. Now, I want to get all 4 cylinders on the screen at once. So to do that, I can go and adjust the time base. Let's try 20 milliseconds and see what we got here. I'm going to let the RPM come down. This is a cold start here. And I'm going to go back into the actual voltage scale here. And I'm going to just select, let's go ahead and select 200 millivolts. I'm just using the force here. It's not quite enough. Let's go with 2 volts per division. All right, so now I could adjust the time base so that I see, but you can kind of see each one of those up and down spikes there, camel humps, whatever you want to refer to them as, is one of the cylinders. Now this is a 4-cylinder. If I had a problem, one of those would not look like the others, right? I wouldn't know which cylinder was causing the problem because I'd need to turn on a second channel. Now normally, for training purposes, I would adjust the time base a little bit to just get 4 of these on the screen. But since I'm about to turn on a couple more channels, I'm going to leave it at this time base for the time being and not make the final adjustment until I got all 3 channels up and running. So the second channel I'm going to turn on is channel B, and I am going to say that, hey, let's go ahead and go with a 5 volt pattern. And you notice here I've got a green channel being displayed now, and it's upside down. So this is the one that's, again, showing me a secondary ignition pattern. So let's go back into channel B there, and let's go to the probe setting, and we're going to hit the invert button. Try to hit the invert button at least. Okay. So now that I got the invert button on, now I've got it so it's flipped. Now I could have did the same thing by taking the actual component and just flipping it around, but it's easy. I'm already at the scope. So now technically I know where number 1 is on the screen. Now I should change a voltage scale because you see it says over range. So I'll do that just to be technically correct. Let's see if 10 volts would be enough. So 10 volts seems like it's enough, but again, all of this right now is just, I still don't have channel 3 hooked up. So I might have to change these scales a little bit more to get a better picture. So I'm going to go ahead and plug in channel 3 to the vehicle. And again, this channel is actually going to be my current probe. So I'm going to turn on channel C. I'm going to go to probe setting. I'm going to select the current probe that I'm using. I'm just going to say, yeah, okay, I don't care about that. All right, so now I got 3 channels. Now, here's the problem. They're all right on top of each other. So like with most scopes, I can actually grab one of these channels and kind of move it where I want it to go so that it's a little bit easier for us to have definition of these different patterns. Now, when I do that, it's not actually changing the voltage scale or time base or anything. So it's not going to say that it's out of range. You're just not going to see the top part of the pattern on some of these, or the lower part of the pattern, depending on where I grab these patterns to move them on the screen. So I can move it, you know, to the bottom part of the screen. I can move it to the top part of the screen. But this is how I could get the different types of patterns on there. And again, I would never go this far normally unless I saw that my red pattern, I'm just going to turn these other 2 channels off again so it's a little bit easier. If that red pattern was not uniform, which this one is, then I would go through those extra steps. And I wouldn't necessarily put on both channels. I'd probably only put on one because all I really need is one type of firing order input, and then I can use this to help me diagnose the car. Because remember, if it's running rough or it's misfiring, it's affecting the exhaust pressure, that pulse of air coming out of the exhaust pipe. So now what I'm going to do is I'm just going to do the same type of test. I'm just going to show you another example that we had in the PowerPoint. I'm not going to go through them all. I'm just going to go to the crankcase, right? So I'm going to take the exhaust, the pressure transducer out of the tailpipe of this car, and I'm going to get some vacuum hose adapters so that when I go over to the actual crankcase here, I'm going to pull the dipstick tube out. Not sure if you picked that up on the audio or not, but because it's mass airflow, once I pulled that dipstick tube out, the engine started to run a little bit rough. And here I'm displaying a crankcase pressure transducer waveform. And again, I'd be looking for something that was not uniform. And I'd take the same series of steps, so if something was out of whack here, again, I wouldn't necessarily know which cylinder was what, so I'd have to turn on channel 2 and get some type of pressure or some type of RPM type of input here for the firing order so I know which cylinders could possibly be causing the problem. Now, one little word of advice. When we're dealing with exhaust back pressure, it's a tube, right? It's an exhaust pipe. So when I look at my actual waveform coming in the exhaust and I hook up to a firing order here, it takes a little bit of time for that pulse of that exhaust pulse to make its way from the engine out to the tailpipe. So again, in the PowerPoint that we shared, we talked about it on one of the slides. If it's a 4-cylinder, 6-cylinder, 8-cylinder, let's say I triggered off number 1 as my firing input, I would have to count a couple exhaust pulses after that because it took that time to go out the tailpipe. Just wanted to make reference to that. So if you guys want to see more information like this, I'll be more than happy to make as many of these types of videos as you guys deem worthy to actually do it. But I wanted to show you some of the advanced system testing, how, more importantly, how my mindset works of using those 6 main inputs to get a diagnostic pathway. We all know the types of tests we're supposed to do to help determine if it's ignition, fuel, whatever, but then using maybe some more advanced testing procedures to get the same test results you want in a shorter amount of time. So hopefully you guys found this useful, and I look forward to seeing you guys again in a future training video. Thanks.